Now, if we're clever, Gauss's law can allow us to work out electric fields with extraordinary ease. It doesn't always work, but when it does, it makes it very quick. And here's one example. Let's imagine we have an infinite plane uniformly charged, and we have a charge at, say, sigma per unit area. Now, what's the electric field near this plane? Well, the first step whenever doing a Gauss's law type problem is work out in words or a picture what you think the field is going to look like. So what's it going to look like here? Well, as this plane is infinite and uniformly charged, the electric field is going to move away from the plane in both directions. You might imagine it might move at an angle or something like that, but that doesn't make sense because this is a symmetrical situation. One part in the plane is just like any other part, so if it was going at an angle, there'd be no reason for that. So what that's telling us is, based on symmetry, the electric fields must go outwards, so it's a positive charge, and they must go straight outwards on both sides. On the other side, they'll be going out like here. So we can work that out just using common sense, and that's a crucial part. Don't just try and use equations, use your common sense first. So because of the symmetry of the situation, the fact that because the plane is infinite, any point in it is just like any other, and there's no particular direction, that means the field must go straight out. Okay, so that's step one, draw a picture. Step two, pick your surface. Whenever using Gauss's law, we pick a so-called a Gaussian surface. And this surface is what we're doing our surface integral over. Now we could pick any shape we like. We could pick some strange blobby peanutty shape, but that won't make the maths very easy. The basic rule is you should pick a surface so that the field is either parallel or perpendicular to every point on the surface. Why do we do that? It's to make the maths easier. Now in this case, a parallel surface would be running straight outwards and a perpendicular one would be flat. So how about a surface something like this? We're going to have a cube coming out of the plane and also extending the other side. So something like that. So we've got a square region of the plane, and we've drawn a cube going straight out from it, and that's going to be our Gaussian surface. Now what we know is that the surface integral over that surface, so the surface integral, which is the electric field for each part of it, dot the normal vector times the unit of area, is going to be equal to the sum of the charges inside. And we know the charge is sigma per unit area, so that's just going to be sigma times the area being this area here, or equivalently that area there, over epsilon naught. Okay, so what is the surface integral? Well, for this long cube we've got the two ends, and we've got four long sides. So we can just add up each of these components. So for each long side, the electric field and the normal vector are perpendicular. So I'd like to take the top here, the normal vector is in this direction, whereas the electric field is in that direction. They're at right angles, so the dot product is 0. So that's what we said by picking a field either parallel or perpendicular. If you've got a field that's parallel, you can just ignore the surface integral. You don't have to work it out because it's 0. So in fact, all that matters is the surface integral over the two ends, because everywhere else that surface integral is 0. And what is the surface integral over those two ends? Well, because the electric field is coming straight out, it must be the same everywhere. The electric field is uniform, and the surface is perpendicular to it. That's the case we did earlier. They're in the same direction, so cos theta Theta is 0, so cos theta is 1. So it's just the magnitude of the electric field. So the magnitude of the electric field times unit vector 1 times the area. So that equals sigma A over epsilon naught. So that means, rearranging, that the magnitude of the electric field, the A's cancel. Oh, one thing I should mention back here, this is the electric field times the area at each end, but you've got two ends, so there should actually be a 2 in front of there. So the mod of the electric field is just sigma, the charge density, over 2 epsilon naught. And that's the answer, which is a remarkable one. It's telling us that the electric field is constant. It doesn't depend where you are. It's always got this magnitude, whether you're close to the infinite plane or very, very far away. And it's going to be the same but in opposite directions.